everyone, welcome back. I guess today is Monday. I don't know, I've lost track, so regardless. Not too many classes left. Let's see, I don't know how many classes are left, but it's not many. All right. Last time we were talking about perturbation theory, and we derived all the equations. They're not hard, and especially for making a first-order correction to first-order perturbation theory, the energy correction is rather simple. And there's lots of example problems we could work on that are hopefully at this point kind of child's play. So what I want to do is go back to looking at atoms and hydrogen atom wave functions because I don't spend a lot of time on atomic or molecular structure, or really any time. So I just want to remind you about how these things work, and this is just a good substrate for that. Okay, so the problem we're solving is helium, the helium ground state energy. You have to use perturbation theory because what we're going to do is we're going to start out with a H0. Let me start writing this down. Let me write down the Hamiltonian. And the H0 component is momentum of one electron, momentum of the other electron. So we'll just solve one of these and multiply by 2 because we're going to put them both in the S state. And let me make a correction that I screwed up last time. 1 over 4 pi E naught, that makes the units correct. They both have a interaction with the nucleus. Minus because the electron nucleus, which has 2 protons, is of course a downhill interaction, which is good. Okay, with this, all I've got, you know what I've got? I've basically got a hydrogen atom wave function for 2 electrons. It's a hydrogen atom wave function with an R1 in one and an R2 in the other, and you just multiply them. As we're going to see, the resulting energy is really off. I think it's too low. Anyway, it's pretty far off. The reason is because the electrons interact. Notice that I don't have a Z here because this is for the nucleus. And we use the absolute value of R1 minus R2, which is R2 minus R1. It's just how close are the 2 electrons. As I mentioned, this, for helium or anything other than hydrogen or a hydrogen-like atom with only 1 electron, destroys your ability to solve the Schrödinger equation analytically. You can solve it numerically, and that's what programs like Gaussian, QChem, there's a zillion of these, James, that's what they do, but they have to solve the Schrödinger equation numerically. There's no analytical solution. Okay, so what we're going to do is we're going to make this our H naught, and the solution are hydrogen atom wave functions. They have a slightly different Bohr radius because a helium with a more positive nucleus causes the electrons to contract compared to a hydrogen atom, which has only 1 positive charge in the nucleus. That's easy to take care of, and I'll point that out in a minute. And this will be the perturbation, which is going to get the energy way closer to the right value, which we know experimentally. Okay, so what do we do? Okay, with this being H0, and again, it is identical to a hydrogen atom, except that you have a more positive nucleus and there's 2 electrons. Those differences are really trivial, by the way. There's no problem fixing that. And what you do is, where am I at? I've actually already lost my place. The total wave function is going to be, because I mentioned last time the Hamiltonian H naught is separable. That's separable, and that means that you have 2 hydrogen wave functions. And so when I mentioned theta 1 and phi 1, that's kind of a joke because S states they don't have angular wave functions. Okay, so there's a wave function for the first electron, and here's one for the second electron. I'm still going to pretend as though that there are angle parts, but there aren't. It's just the angular wave functions for S states are just constants. Normalization constants is all they are. Okay, but I don't want you to forget that there is still an angular part. Okay, so, and actually here now, I'll explicitly point that out. The radial part of each individual wave function. So remember, I'm now talking here. It's like I'm going to talk about the first one. It has a radial part, and that is e to the minus z over a naught. A naught is a Bohr. I'll call that R1. A naught is a Bohr. That's half an angstrom. So in hydrogen atoms, about half an angstrom. And for helium, with the 2 plus nucleus, you'd have, instead of minus R1 over A naught, it's minus 2 R1 over E naught. So that represents the contraction of the 1s orbital due to the fact that helium has 2 plus nucleus. It's real easy. It's real easy. It affects the normalization as well. That's why I put a little twiddle there. There's a normalization constant. Okay, in the angular, this is kind of important. The symbology is a Y, and I've already lost again. You usually write L and M. In this case, L and M are both 0. And here, it's not sort of, it is. It's 1 over the square root of 4 pi. So anyway, so those are the radial angular wave functions for one state, and the other state's the same, except it has an R2 instead of an R1. Right? So, all right, so not too bad. And how you solve that, that's something, and that's not something I would know or even want to do. Let's see here. And okay, now, of course, we have to address the normalization. And I said last time, we need to talk about normalization, because you have to be really careful about these atomic orbitals and making sure that they're properly normalized. If not, then everything's going to be screwed up, right? Because we're solving expectation values. When you do expectation values, the normalization has to be correct. Okay, so what is the normalization? Okay, so maybe I'll put this in a homework and you'll have to do it. Normalization means that everything integrates to 1. And so what are we integrating? Well, we're going to integrate 0 to infinity. We're going to integrate the radial part. So I'm breaking this up into a psi r, psi theta, and psi, well, sorry. Psi r, I'm going to have a little y for theta and phi. That's the traditional how that's expressed. So I'll do r, and I'll do, doesn't matter whether it's R1 or R2, sorry. Okay, as you roll the wave function squared, now we know about that. R squared dr. And now you should already be like, wait a minute. You should be saying that, because where's my 4 pi? 4 pi r squared is the Jacobian, but I wrote an r squared. The reason is, when you look up where Jacobians come from, the 4 pi comes about from the angle parts. So when you go from xyz to r theta phi, you have to have a Jacobian to correctly represent volume. And you get an r squared for the radial part, you get a 4 pi for the angle parts. Because you usually just integrate the Jacobian and you get a 4 pi. You can't do that when you have atomic wave functions, because they have angular wave functions. You can't just integrate them as though they're not there. Now, let me show you what that means. So I've integrated the r, and now I've got an integral for theta. Theta goes from 0 to pi, and phi goes from 0 to 2 pi. And so now you've got to integrate the wave function, the radial wave function. That's the angular wave function. And don't forget that there's a sine theta that comes from the Jacobian. And let's see, theta goes with 0 to pi. Hopefully I'm getting that order right. And phi goes from 0 to 2 pi. Okay, so again, I did not put a 4 pi here. I know it's 4 pi r squared, but the 4 pi comes from doing this integral without a wave function. If I do this without a wave function, I get a 4 pi. That's where 4 pi r squared comes from. But I can't do that because I need to think about whether there's something there to integrate, right? So this has to be 1. So when you look up wave functions online, you need to double check this. The reason is, here, let me show you what you can get. The answer is, for S states, as you've seen, the angular wave function is actually just a constant. What that causes people to do, people forget that it's there. So all this stuff I just told you, people very frequently forget that that's a thing. And I actually am not keeping track of time. Okay, so I have to go anyway. So people will forget that you have to do this. And as a result, let me put a question mark here. As a result, sometimes people do this. Now again, the point of the fact that there's a problem is when there's no angular part, because you're talking about an S state, and therefore you want this to be true. When you look online, people know that you're often going to do this, so they use a normalization that makes this true. But notice that this will not have the same normalization, because heads up. Without the wave function, you get a 4 pi, but look at what the wave function squared is, 1 over 4 pi. See, the 4 pi is not there. This part kills it. And that means that this is going to have a different normalization than this would, because there's a 4 pi there. This is ultimately not correct, or it's not robust. But a lot of people are they're just geared to do it this way, and a lot of wave functions you find online are normalized this way and not this way, whereas you really should be doing it this way. Anyway, you've got to look out for that, because when I find things online, I never know which one I'm going to run into until I double check. Okay, so let me see. In this case, so call this case 2, case 1, see, case 2, what you get is the radial wave function is 1 over the square root of pi, z over a naught, the Bohr 3/2, e to the minus z over a naught r. Okay, so in case 2, you get this, but in case 1, which is the one you really should be doing, you get a different normalization constant. Notice that you're playing games with 4 and pi. Okay. Now the way to do this is you just check how it normalizes. Does it normalize against 4 pi r squared, or is it just r squared? That's how you know which one you're dealing with. Anyway, just wanted to point that out. It is kind of horribly important. Okay. All right. So let's start addressing the problem with not including the electron-electron interaction for a helium ground state. Okay. So where am I at? Okay. So the energy. We're not going to worry about the wave function. We're going to worry about the energy, because that's what we really want. And you can measure the energy of a helium atom. And what does that mean? The energy of a helium atom is how much energy it takes to blow off the 2 electrons. That's what I would call the energy of a helium atom. That will be the energy of a Hamiltonian that is all about the electrons and the nucleus. Okay, now I'll give you the experimental result a little bit, but if we ignore the electron-electron interaction, you're going to get a number that's way too low. Okay, so you get 2, and this is because there are 2 electrons. Okay, so don't forget where that comes from. Okay, then you get z squared. Now, z squared comes about from using these wave functions, right? So this is a generic wave function that's hydrogen-like, but can have a different nucleus. Z is 1 for hydrogen, 2 for helium. Anyway, that's straightforward, right? So it affects the energy. Okay. Now, of course, if Z is 1, you better get minus 13.6 eV, often referred to as EH, energy of a hydrogen atom. So that's what you need to be getting if Z is 1. Okay, now again, I've got 2 electrons. I'm going to say that Z is 2 because we're doing helium. Helium has a 2 plus charge. And what you get is minus 108.8 eV. Okay, so again, this is the unperturbed, this is the H naught result. The part with the electron repulsion missing. Electron repulsion will raise this up. It'll be less negative. Actually, it's around minus 78. So in terms of how far off is it, the real answer, I think, is around minus 78. I have it here. Anyway, we'll see it in a minute. I think off the top of my head, it's around minus 78. It's pretty far off. I mean, that's actually pretty bad. Minus 78 versus 108, that's way off. That's hideous. Okay. Okay, so now what I need to do is I need to add this, and we just talked about how to calculate this. I'm going to do the expectation value of the potential, which of course looks something like this. Gotta draw the line again. Okay, it'll be double integral because I have R1 and R2, so I'm going to integrate R1 and R2. It's going to be wave function 2, over so I forgot whether I'm doing 4 pi. What am I doing? 4 pi or not 4 pi? I think no, I'm not using 4 pi. Looks kind of bad, right? But we know we just plug it into Mathematica. Oh, there's supposed to be a little in the bracket. Oh, God, there's little stars, right? Complex conjugate on the left, normal functions on the right. But these are fully real, so you don't actually have to worry about that. This certainly looks like a lot, but I know that the hard part is simply just programming it into Mathematica correctly and hitting go, and sometimes waiting maybe 10 minutes because this looks kind of bad. But there's something else. Now, this is the reason I really wanted to talk about this. I want to give you something for your mathematical toolkit. Double integral. I kind of hate double integrals because I keep, like, wait a minute, how do I do double integrals? I keep forgetting. So don't worry about this. I'm going to do an aside. I'm even going to color the aside so that you make sure that you understand that I'm just blabbering. Okay, double integral. Let's do dx dy. X over y. All right, I look at that and I'm like, wait, I integrate x and then I integrate y. Nah, it's not hard, right? It's integral of x dx, 1 over y dy. And so that's, of course, 1/2 x squared ln y. Okay. Oh, I didn't even look at my notes. I guess that's right. Okay, now do this one. Ta-da! How are you going to do that? How are you going to do that? Remember, you've got to have your x's here, and you got to have your y's there. They got to be separated. How do you separate that? How do you separate 1 over x minus y? Maybe write it down as a series? Good. That's a good start. But I want to point out this is not straightforward. And this is very straightforward. You just got to remember that. The only hard part is remember that you just separate the 2 integrals. In other words, it's the easiest possible approach is the right one. Here, yeah, you do 2 different integrals, but integrals of what? How do you can't have y's in this x and you can't have x's in this y. That doesn't work. The x's have to be here and the y's have to be here to be there, and I don't know how to do that for this. That's kind of a major problem. Oh, let's not forget this absolute value. Actually, here, let me go over here and let me start addressing the problem of this. How do I'm going to have to change this. I'm going to have to represent this. I'm going to represent it as a series. And then this immediate 1 over problem will go away. Anyway, I'm getting ahead of myself. When you look up papers on how you do these type of Coulomb integrals, you're going to find this, that the absolute value is R1 squared plus R2 squared, so plus minus 2 R1, R2 cos angle between. Kind of a mouthful, isn't it? Okay. Still, same problem, actually slightly worse. But it turns out this thing is equal to this. You write it out as an expand, like a Taylor series, except that you're not like expanding in like X or Y. You're going to do this. I have no idea how anyone figured this out, but whatever. You may notice I'm writing, let me put this out. That's R less and R greater. I'll explain that in a second. And then you've got, okay, so what the hell is this? All right, well, let's go through this. Okay. We're going to integrate 1 over R1 and R2. So, and this is going to, let me just write this down. R1 is greater than R2. Then R greater is R1. And if R2 is greater than R1, then R greater is R2. Okay, so it's obvious, right? And then R less, R greater, R less would be R1. All right, so that's relatively straightforward. Okay, P sub L, oh, here, I'll write X instead of cos. Is that what I'm doing? Okay, these are Legendre polynomials. Legendre polynomials, the solution to a couple of differential equations. Anyway, so you look these up. And instead of X, you'd have cosine, but whatever. So P0 is 1, P1 is X, P2 is 1/2 X, 3x squared, sorry, 3x squared. Anyway, all right, so you can look them up. All right, so what do we got? All right, I got this thing. And now, instead of this, I'm going to write this. I'm certain I can just probably write out a couple of terms. I can go to maybe L of 5, and I probably don't need to worry anymore. And you'll see that's actually more true than you think. Anyway, so I get that. I can just write a couple of terms. But R less than, R greater than, you need to be integrating with R1 and R2, not R less than and R greater than. All right, so that's a little weird. And of course, it sucks that it's a series. So that means that your one integral turns into, like I say, if I go to L of 5, then you have like 5 integrals instead of 1. Okay, but whatever. You know Mathematica is going to deal with it. Okay, so now I got to start whittling it down. And I got one more thing to tell you. About this. I'm going to go this way, and then I'm going to start. Then I'm going to do this guy. I'm going to do this guy. I'm going to write all of this out. It does go across the board. It's really awful. I actually did it all on Mathematica too. Maybe I'll put that on the homework. Okay. There's this thing called the Spherical Harmonic addition theorem. It surprisingly comes up quite frequently because Coulomb interactions come up quite frequently. You're often integrating things. You're often integrating Coulombic interactions. That's quite a frequent thing. You have to do it this way for all the reasons I just said. But it turns out that rather than dealing with this, it turns out that a Legendre transform itself can be written as a series of spherical harmonic wave functions. So you're going to gain, here, I'll write this part out. Greater to the L, or less to the L plus 1. Okay, it turns out that the Legendre polynomials can be put in a Taylor series form. 2L plus 1. Plus a little bigger. There we go. 2L plus 1. Okay, now I got another sum. So now I got a sum of the sum. So that does not look great. M equals minus L to L. And you've got, here is a spherical harmonic, which of course is going to be functions of theta and phi for one electron. And here is the other one. It's not the complex conjugate for whatever is your other guy, your other electron. Okay, so again, we talked about greater and less than, some constants as we do the sum. So we got a sum within a sum. So it's like, man, we've already talked about 5 terms, so maybe 5 terms in L, and then we'll do maybe 5 and 8. So now we've got 25 integrals as opposed to just 5, as opposed to just 1. If we never did any of this, but you have to. Anyway, so why am I doing this? Now I've got a sum of 5, and within every sum there's another sum, and if you want to be super accurate, both of them go to infinity. So it looks like I've made it worse. All right, so the next thing is I'm going to write the whole thing out. And this is where I got to remind you that you're the ones who want PhDs, right? And you signed up for this. And if you can hack this, you're valuable. And there's a lot of value to being valuable. I'm talking about money. All right, so let me write this whole thing out. And also note that if you are in a situation where you have to solve this, it's your job. You probably, whatever, situation finds you needed to do this, it's probably like job oriented. You probably have a few days, so you can do this. Okay, so I'm going to do the Coulomb integral, the perturbation theory. I'm going to write the whole thing out for 2 electrons. Okay, and then of course we'll just focus on some of the individual integrals. Anyway, here's the thing that's kind of painful. All right, so I've got r theta and phi, 3 integrals, but I have 2 electrons, so I have 6 integrals, right? Okay, so let's do r from 0 to infinity. So I'm going to do it that way. Theta goes from 0 to pi, and phi goes from 0 to 2 pi. Already looks quite off. Okay. So again, and I'll put these up front because otherwise I'm going to get confused. D theta 1, d theta 2, d theta 1, d 2. I'll worry about the r squareds and sines later, the Jacobian bits. Okay. All right. Now let's put down the radial wave functions. R1, R2. Okay, not too hard to have Mathematica deal with that. Okay, now there's no 4 pi. That would really be 16 pi squared, but because we're not using the 4 pi r squared form, so we're just multiplying that by r1 squared, r2 squared. Okay, now that's it for, okay, I've represented all the integrals and the partials. I've taken care of the wave functions, the Jacobian r squared. Now we've got to start dealing with the Coulomb operator. Since it's not a derivative, I can write it. I don't need to like sandwich it in between. There's no derivatives. They can appear wherever. So I'm going to write them off to the right because it's going to kind of decomplicate things a bit. Okay, I've got this. Did I write? Wait, did I put? Did I put R? Sorry, when I first wrote that, it's R less than. Sorry, you see up there, I wrote that wrong. Sorry about that. It's R less than. Sorry about that. R less is on top, R greater. I messed that up. I messed that up when I was talking about the spherical harmonic addition theorem. Sorry about that. Anyway, R less is on top, R greater is on bottom. It's kind of kind of naturally sensible. Sorry about that. Anyway, okay. I've done this right. Okay, then I've got 4 pi. Computer can deal with 4 pi. 2L plus 1, that's not hard. Okay, now I've got the sum. All right, for any L, for any value of L, I've got the sum that's going to, from n is minus L to plus L. And we know that, S has L of 0, so M is 0. P's have L of 1, so M goes from minus 1, 0, plus 1. So I get this. I fundamentally understand why there's 3 of these. Px, Py, Pz is what they're doing. Okay, now I've got to include the wave function of the first electron, and let's do the angular addition whatever thing. It's spherical harmonic. Now let's do the second wave function for the second electron. Again, it's 0, 0. It's an S state. And then here's from the angular addition theorem, the other harmonic. Okay, then I've got, oh my God, look at this. Sine 1, sine 2. Oh yeah, that's, look at this big. You're the ones who wanted PhDs. Okay, here's the trick. You're not going to believe this is going to be so funny. Let me make sure I know where I got my notes. Okay. Look at this bloody mess. All right, you got a sum of sums. But now I knew, even when I was reading up on this the first time, I knew that this would actually simplify hideously. The thing is, spherical harmonic wave functions, we know that those are eigenfunctions of Hamiltonian. Remember, we did them at the very beginning of class when we were doing particle in a sphere. We found out that spherical harmonics are the angular wave functions. Wave functions squared and integrated are either 1, when the wave function is itself, the complex conjugate times itself. It's normalized, so it's 1. But if you get a harmonic wave function that's not the same, then you get 0. That's orthonormality. So here's my point. The S states, the wave functions are constants. So that means that when you're integrating it against another harmonic, that harmonic has got to be a constant too. Because if it's anything else, if it's any of the excited states, anything other than an L equals 0 state, you're going to get 0. Just the same way that, because wave functions are orthonormal. Unless this is the same as that, it just integrates. If it's the same, it'll integrate to something. If it's different, it'll integrate to 0. So, in all of this junk, because it's being integrated, only L equals 0 survives. And I'm talking about L equals 0 right there. Right at the very front. So there's no sum. Just do this for L equals 0. Notice there's no sum there either. Right? From M of 0 to 0. There's no sum. So all of this just simplified to almost nothing. Okay, so what does that have? What does that turn into? Okay, let me write the damn thing again. Oh, damn it. You know what? 4 pi E naught. Yeah, sorry. There's a 4 pi, God, sorry, the Coulomb thing. I forgot about the Coulomb constant. Oh, they're not my notes. I screwed up. Sorry about that. Okay, so now let me do this again. 4, 5, 6, 0 to 2 pi, 0 to pi. Okay, so I'm going to simplify this. dr1, dr2, d theta 1, d theta 2, d phi 1, d phi 2. Okay, so I haven't simplified it too much yet. You know what I'm going to do? I am going to yeah, I can. I'm sorry, I just got a little lost in my notes. I can figure this out. I didn't mean to write out the whole thing, but I'll write out the whole thing. So anyway, I'm committed now. Okay. So it turns out. So I've got, now what? 1 squared, 2 squared. That could actually, that 1 over 4 pi is not going to go all the way to the very front. Okay, so there's only one term. Now I've got r less than to the 0, so there's nothing there. R greater than to the 1, right? So I'm saying only L equals 0, so that's what that does. So it's just 1 over R greater. Now, of course, now I'm going to have to figure out what to do with R greater. L of 0 times 4 pi. 4 pi over 2 times 0 plus 1. Okay. Now, what is all this going to? Okay. Let me actually go back here because again, this is obviously hideous. Let me go back here. All right. So what am I going to get? This is 1 over 4 pi. Now I can remember that the only L of 0 and the L 0, 0, the spherical harmonic is 1 over the square root of 4 pi. This is 1 over 4 pi. This is 1 over the square root of 4 pi by definition. Okay, these things are going to integrate with the d thetas and d phis to 4 pi. That's where the Jacobian 4 pi comes from. There's 2 of them. Okay, so again, I'm just plugging in spherical harmonics. The spherical harmonic L0, M0 is 1 over the square root of 4 pi. So that's squared. 1 over the square root of 4 pi. No, 4, not 1. No, 1 over. Sorry. No, wait, did I do that right? No, I did that right. Sorry. God. Okay. And again, after the integral, remember if you're integrating sine d theta d phi from 0 to pi, 0 to 2 pi, you get 4 pi, right? 4 pi r squared. So these are going to integrate the same. So that wipes that out. Now I'm left with a 1 over 4 pi. There you go. Go ahead and explain that. Kind of tough to follow, isn't it? Oh, and now I can get rid of these. There we go. Try writing that down in your notes. There you go. Not too bad, right? So I told you, I mean, it's like ridiculous how much this simplifies. All right. I know it's not easy to see, but so now let's start on how to solve this thing. Oh, here. There we go. All right, now that does not look nearly as bad. You got it. But now I've got, here's the problem. God, look at that. It's almost actually done. I mean, this normally, Mathematica would have no problem with this. Except now I got this R greater. Oh, I don't have an R greater. That's to the zeros. I have this R. Sorry, I have no R less than. I have an R greater than on the bottom. So what do I do with R greater than, which may or may not be R1 or R2? This is clever. I came up with it. I wrote it down on the webpage. Okay, so what you're going to do. Now, again, as usual, you've got to break up. let me take the 1 over 4 pi e naught. And we're going to integrate R1 from 0 to infinity. Let's see here. I've got wave function squared. And so I have deleted the wave functions a while ago, but let's see, I have got e squared. Oh, I've got the, oh, god damn it, I forgot the e squared, sorry, electric charge, which goes with that. Okay, I forgot about that. Okay, the normalization. Oh, okay. It's 2. I'm using. Now I remember. I had to just think about which wave function I was using. I was using. I told you there's 2 wave functions. I'm using the 2 z over a naught to the 3 halves. Right? But then I have to square it, right? So 2, because I have to square the wave function. 2 squared is 4. Okay, then I've got z over a naught to the 3 halves, and I'm squaring it. Z is 2, so 2 to the 3 is 8. Okay, anyway, just look at what I wrote for the wave function. Okay, z over a naught to the 3 halves squared is 2 to the 3, which is 8, and I've got a naught to the 3. All right. Electric charge squared, 1 over 4 pi e naught. E to the minus z minus z r1. Z is 2, but I'm squaring it, so that's to the minus 4. R1 over a naught. Okay. Now check this out. Now I'm going to write the other integral. Now here's how you're going to do this. Remember, when you've got a double integral, you just get one integral times the other integral. Sorry, Jesus. Okay. Times the other integral. Now here's a trick. I wrote a bracket because I'm going to do is I'm going to break up the R2 integral into 2 pieces. The first one, I'm going to integrate from 0 to R1. I'm going to integrate R2 from 0 to R1. Meaning R2 is always less than R1. Good, isn't that neat? Okay, same normalization for 8 over a naught to the 3rd. E to the minus 4 R2 over a naught. Okay, let's see here. R2 is always less than R1, so 2 squared over R1, and I think that's it. What's going to happen is that's going to have to, so when I multiply, I'm going to multiply this integral by this integral, and then this by this one. Okay, so then I'm going to integrate from R1 to infinity. All right, you see 0 to R1, R1 to infinity. So I'm integrating all the way to infinity. Again, just broke up the integral in a very standard way. All the rest of this is the same. Okay. Okay. Now, R2 is greater than R1, right? R2 is by definition greater than R1. And that makes that R2. R greater is R2. All right, you see that? R2 squared over R1, but here, but in this one, it's R2 squared over R2, so it's just R2. All right. Now, the only thing I can imagine might be a little confusing is that there's an R1 here and the R2 integral, but it's just a constant. It can actually come out from here. All right, let me just show you what that looks like. And Jesus, I'm almost out of time. I didn't mean to spend so much time on this. But again, these are one of the, I really wanted you to see this because, you know, you have to be okay with being confronted with an equation that's 10 miles long. Now, we got lucky because of the fact that we're dealing with S states, but you may have a situation where you just simply have to deal with a 10-mile-long equation. You've got to be able to do it. Anyway, but that's not today. Okay, so what do you get? You get mean squared. It's still going to be kind of long. Okay, so here to infinity. What's 4 times 8? 32. A naught to the third. Okay, R1, dR1 times the integral from 0 to R1, 32 over A cubed, 4R2 over A naught. Okay. Again, this is the one where R2 is less than R1. So it's the Jacobian's R2 squared and the R greater is R1. So that's why R1 is, it's not R1 squared, it's R1. You literally can slide it out of that integral and put it in here. That's exactly correct. It's not like a wink sort of. Okay, so don't forget, remember that's the charge of an electron squared. I'm going to write the whole damn thing again. Kind of obliged. My handwriting is sucky. Okay, now I've got R1 squared times. What did I? There we go. E1 minus 4R2 over A naught. I should look at my notes sometimes. Okay, R2 dR2. So in this one, where R2 is always greater than R1, we have R2 squared over R2. So there you go. And of course, then the Jacobian for R1 remains the same. And so, short of something stupid, I think that this is like literally 100% correct. All right. Mathematica. Do the Mathematica. What you end up with is, now heads up, when you look this up, you will almost never see 1 over 4 pi E naught. People like to simplify things. Charge of an electron. You literally just see 5e squared over 4 over 8a naught. That's the first one. Now, of course, charge over distance is not energy. That's why you have to have 1 over 4 pi e naught. Now, it turns out, now get this, I think it's a coincidence, but the integrals are the same. The two integrals are the same. This is 34. Then you got to plug in. I always plug in SI units, then I convert to EV. Therefore, the total energy is the unperturbed 108.8 EV plus 34 is minus 74.8 EV. The experimental is minus 78.6 EV. Okay. So, there you go. This is a goddamn nightmare, wasn't it? Anyway, so, terribly wrong. You can never ignore electron-electron interaction. That's absurd. The first order, look how close we get. I think it's about 2%. About 2%. No, that's a lot more than 2%. Anyway, 4% about. Anyway, obviously, 74 from 78 is way, way, way closer. So there you go. That's perturbation theory. That's how it works. Mostly, I want you to get sucked into atomic orbitals. deal with those equations that go 10 miles long, because as much as that sucks, it's worth a lot of money. And I'm going to leave you with this, because I think I'm out of time. I want to point out that that number is technically higher. That actually is terribly important. We're going to cover this, what is today, Monday? I don't know what today is. Whenever we meet again, it's actually really important that that number is bigger than this one. I mean, that's really important. And I'm going to explain why that is. And it's something you need to look out for. Whenever you're trying to calculate things for molecules, you're almost always going to you have to use approximations for all the reasons you just saw. You need to have a number, an energy that's always higher than the real value. If you don't find that, you've done it wrong. It's something to look out for. Why that is, I will explain next time. So, I hope I haven't traumatized you too bad, and almost done. All right, I'll see you all on Wednesday.